All right, so welcome to Math 408, L functions and sphere packing. This is our second to last class. And so what I want to continue doing is, showing you what tools come into play in the main proofs. And if anybody is interested in continuing this, next semester, either as an independent study or as maybe a paid research assistant, let me know. I'm happy to continue. There's a tremendous amount of material. And what I love about this problem is how many great things it's connected to. And so today I want to concentrate on one of the last two things that I want to get on your radar screen. And I will save the other item for the final day of the semester. Okay, so what is your first thought when you see the title of this paper? Or this slide, the abstract, or the table of contents? What reaches out to you? Something should be going through your mind when you look at this.
They talk about Poisson summation and some of the stuff we've done.
Good. So it mentions linear programming, mentions Poisson summation. We can see a lot of our stuff coming in. But there's something else that should be, grasping your attention, screaming out at you.
It's an upper dimension or upper bound thing rather than lower bound.
There is that, but there's something else even more basic. Go to the very beginning of the slide.
It's new.
Okay, go to the other end of the title.
It's number one.
It's number one, right? So this is, obviously the first in the sequence of works being done. It's always interesting when you have a title like this. There's a series of phenomenal papers by Hardy and Littlewood on partition problems. And your partitio numero 1, 2, 3, et cetera, et cetera, et cetera. And so what they're going to do in this paper, they're going to develop some of the tools and techniques and see some of the consequences in trying to find optimal sphere packings. And so what I want to do is I want to go through some of the key ideas that they're going to be using. And so again, a lot of these, as you've noticed, are things you've seen before. And part of this is to just give you a sense of what is out there mathematically, what might you want to study, and what can you actually do with this. When I was an undergraduate, I will admit that I was upset anytime there were extra conditions put on theorems. I always wanted theorems proven in as great generality as possible. And it wasn't until I got to grad school that I realized, well, of course my function is Schwartz space infinitely differentiable with rapid decay. How could I ever look at anything else? And it's the difference between just doing math and doing math because you have an application in mind. And so when you start having an application, it's often very different because you just care about, is my theorem general enough to cover the situations that will be arising? Okay, so just two snippets from the beginning of the paper. The first is they talk about how in dimensions 8 and 24, the bounds are extremely close to the densities of known packings. They're too high by factors of essentially 1. And so they believe that their techniques can be used to prove sharp bounds in dimensions 8 and 24. They're not missing by much. And you can see that this is significant improvement over what there was before. And that's one of the things I want to talk a little bit about today is how do you measure different quantities, different results, and get a sense of the caliber of the result, the difficulty of the improvement. The other thing, just very early in the paper, is linear programming bounds can be indeed, and so again you see that linear programming is one of the key ideas. It's in the first line on this last paragraph, and it's also in the last line. All right, so here is a plot of the upper curve is the previous upper bound by Rogers. The lower curve is their new upper bound, and the bottom line are the best known packings. How good of a job do you think these bounds are doing?
I think pretty bad for dimensions other than 8 and 24.
I think you're being a little bit too harsh when you say other than 8 and 24. There's something other than 8 that works as well, but it's not so bad.
Lower dimensions are pretty good also.
Yeah, lower dimensions are pretty good. Up to dimension 8, it's not bad. And then it's fascinating how well it does at 8 and 24. And then it just takes off. And one of the questions is always just trying to get a sense of, well, how much of a difference is there between these different curves? And when you look at it, it doesn't look like there's that much of a difference between the two curves initially. But when you look on the data table on the right, you can actually see that there really is more of a sizable difference between the two. And if you look at the formula that's going on, the plot of the log base 2 of delta plus n 24 minus n over 96 versus the dimension. And so one of the things I've been talking about all semester, or for those of you who have had me since the start of your college career, your entire college career, is what should you always have a Pavlovian response to do? When you see something, what should your automatic response be?
Generalize.
Well, there's generalize, but specific type of expression, whenever you see this expression, you should apply this function to it.
Log a product.
Log of products. When we're trying to get a sense of how good are these improvements in the bounds, if you look at the plot, it doesn't seem like it's that phenomenally better as you go further out. When you actually look at the numbers, you see that there is a significant improvement. We're not just talking about a little bit, it's more on a percentage scale. And so I thought I would just, show, since I've been talking about logarithms for so many years for some of you, just show a couple of log scales. The first, anybody know what scale this is?
Richter.
Is it a Richter scale?
The Richter scale to measure earthquakes. And so moving up 1 unit on the Richter scale is a order of magnitude stronger. And so, a 7.8 is very different than a 6.8. And so here's a nice plot that just shows so many different things all at once. It talks about the magnitude and the energy release. It talks about how many earthquakes you have of a given magnitude. And it has a couple of key events in world history. I'm not quite sure why the word equivalent is spread out so much. Maybe that's due to some geological activity. Anybody know any other logarithmic scales?
Decibels for sound.
Excellent. And in fact, that is the very next slide is the decibels for sound. So your 30 is your soft rustling, going up to normal conversation is around 60. Some of my colleagues are probably more like 75, vacuum cleaner, going all the way up to, gunshot at 100 feet. Oh, sorry, siren at 100 feet. Anybody know any other scales that are logarithmic?
Like absolute and apparent magnitude in astronomy.
Okay, good. That is actually the last slide. There was one I had before that.
Mohs hardness.
Which one is that?
Is that logarithmic?
I think it is. I'm not sure.
Wait,
It's
what?
not
A
linear.
diamond is
pH.
like an
pH.
Okay, pH was the one I was thinking of. But what was the one you were thinking of?
I believe the hardness scale is logarithmic. I think a diamond is like 10 times harder than a 9.
Ah, okay, that would make sense. That would be another natural one. And the whole point of this is you want to be able to have objects that have a tremendous spread, be in some sense, you can talk about them all at once. And so is some objects from the universe going from the observable universe is about 10 to the 27 above the human scale. The Planck length is 10 to the negative 35. So an interesting question is, looking at the various things to just try to get a sense of how far they are. This is something we can plot. This is covering approximately 60. But in terms of orders of magnitude, 60 orders of magnitude is tremendous. So I was talking with Professor Strock recently, and he was sharing with me an interesting problem. If you have a piece of paper, how many times do you think you can fold that piece of paper?
7.
And why 7?
I've tried to fold a piece of paper more than 7 times before, and it was hard.
It starts getting harder and harder.
Yeah, because you're doubling the, the paper size.
Doubling the paper size. And so Imagine you were very strong though, you kept folding and folding and folding. Do you think you could do this indefinitely?
No.
Why not?
It's got to stop at some point.
Okay, why?
Reach the size of the observable universe after probably like 100 folds.
Yeah, so that's a question. What he told me is that after 33 folds, it'll be the size of the Earth.
If you fold a paper in half,
And fold that in half and fold that in half.
how is it getting bigger? I don't understand.
Well, just when you fold it in half, you double the thickness.
The
Oh, it'll get
thicknesses
thicker.
of the
Okay.
Earth, but like it's very tiny probably because
Yeah, at
you
some
don't have that
point it'll
much
just
paper.
be be one atom thick. It's very
Because
long
when
the
you
other way.
fold it, you put one half on top of the other.
Yeah.
And so the paper, the height is going up by a factor of 2, and maybe the width is decreasing by a factor of 2. So as you keep doing this, 2 to the 33 is the same as 2 to the 10th to the 3.3. 2 to the 10th is about 10 cubed. So we're talking about 10 to the 9.9 or about 10 to the 10. So you're basically expanding it by a factor of roughly 10 to the 10. It's nice to have some rough sense of the size of objects. All right. So the next item is something we've been talking about throughout the semester. You're given a lattice. The dual lattice is going to be all the vectors such that the dot product is an integer. And then we will be looking at radial functions, and the Fourier transform of a nice radial function can be given by just integrating your function against a Bessel function. And the Bessel function is one of many special functions. A tremendous amount is known about these special functions. And if you go into the subject of number theory, you end up becoming extremely familiar with their properties, with their decay rates, with integral representations. And the idea is to try to use this to get some information about your function. All right, so we will only be needing to look at a very special set of functions. This is similar to the admonishment I was giving earlier. So an admissible function will be a function that has sufficient decay. And so what is sufficient decay? Well, basically we just need something that it's going to allow us the Fourier transform to converge, certain sums of function over the lattice to converge, infinite sums, certain infinite sums involving derivatives. And this is extremely similar to what we saw before. This is almost what we saw before. We have a negative n minus delta, where delta is something greater than 0. Is this exactly the same as what we had in one dimension? Essentially, seems to have gone forward. Essentially, yes. In one dimension, we wanted the exponent to be a little bit more than 1. So we had 1 over 1 plus absolute value of x to something greater than 1. And now we're just adjusting this because we're now in n-dimensional space. And the idea is we want some version of Poisson summation to hold where we're summing a function over the lattice. And we replace that to summing our Fourier transform. All right, so one of the big theorems in the paper is theorem 3.1, which says suppose we have a nice function, so f and f hat are nice. We want f of x to be non-positive when x is greater than or equal to 1. And we want f hat to be greater than or equal to 0 for all t. And then from this, we get some bound on the density of sphere packing. And so it all comes down to, can you find a good function f that has these properties? And it is unfortunately possible that maybe your properties are inconsistent. And so it's not always clear that there will be such a function. But any function you find will give you something. This is a great area of mathematics for the method of divine inspiration. So does anybody know how the method of divine inspiration works?
You just say it.
Yeah, basically, you just say it and you write it down, and it doesn't matter where it came from. You were divinely inspired. You write it down, and so long as it works, it works. You could prove the quadratic formula by just writing down the 2 roots and multiplying everything out and foiling it. You could do the same for the cubic or the quartic. There will be issues in terms of your understanding and whether or not you can generalize it, but it's perfectly fine to just write down the answer. Unfortunately, if you just write down the answer, you may not be able to push it further than what you have. But a lot of times we can actually just play some games and try to see, can we find a good test function? You know, there are some natural candidates to consider and see if any of them work out. And if they do, you then have something that you can try to see, can we do something a little bit better? Okay, so then they go through and they say it's enough to do this for periodic packings, and then they basically start to use the Poisson summation formula and they try to rewrite things. So, you know, again, things we've seen before. The next item is, you know, trying things in one dimension first. As a rule of thumb, it's a good idea to start in an easy case and build intuition. The challenge is sometimes the easier cases are so simple that you don't see the real features of the problem and you can be misled. And so here, does anybody know what chi of -1, 1 is?
1 in that region, 0 elsewhere.
Perfect, it's the indicator function. It's 1 for x in that region and 0 otherwise. And so if you look at this function is clearly going to be positive up to 1, it'll be 0 at 1, and then it'll be negative beyond that. So you can then look at its Fourier transform. Its Fourier transform, this is extremely famous, is the sine of pi t over pi t squared. And that is clearly non-negative. What's the only danger point for looking at sine of pi t over pi t squared?
0.
Okay, so how would you evaluate it at t equals 0?
Take the limit.
Okay, how do you take the limit?
Well, we know that limit sine x over x goes as x goes to 0 is 1. So
I forgot that. How do we know that?
You can just write sine as a Taylor series.
Just say it.
Well, and so I have one answer is to write sine as a Taylor series. Okay, how else could I do it? So that's the only way you would know how to evaluate sine of pi t over pi t is Taylor series. There's nothing else you've learned.
I mean, near 0 is just equal to 1, right?
Right, but why? So one idea was to use Taylor series.
L'Hopital.
Okay, another is to use L'Hopital. So if you want to use Taylor series, what do you need to know in order to use Taylor series?
The derivatives.
So you need to know the derivative of sine. If you want to use L'Hopital's rule, what do you need to know?
similarly, the derivatives
Of sine.
each of the, yeah.
How do you calculate the derivative of sine of pi t?
Derivative of sine is easy to do with Taylor series, so I do
Well,
like
But you can't do Taylor series.
You need to know the limit is 0.
You need to know the limit is 0.
Because it depends on how you define sine. Like if you define it geometrically, you can do it geometrically.
Right, so the problem is, if you want to use L'Hopital, you want to look at, the limit, let's say x goes to 0 of sine of x over x, and you want to say that that's the limit as x goes to 0 of derivative of sine is cosine x over 1. But you need to know that the derivative of sine is cosine. And the way you find this is the limit as h goes to 0 of sine of x plus h minus the sine of x over h is the limit as h goes to 0. I can write the sine of x plus h as sine x cosine h plus cosine x sine h minus sine x over h. And for this, I'm just using trig rules.
Okay, but how do we know we can do that?
That you can prove elementarily. So you can prove that by looking at here's x, here's y, and you can look at angles coming down, like this. You can prove this elementary. That's not a problem. And then you can write this as the limit as h goes to 0 of sine of x times cosine h minus cosine of 0 over h. I'm writing here sine of x times cosine of 0, because cosine of 0 is just 1. Minus, I'm sorry, this is, yes, I'm sorry, plus, and then I can pull the cosine x out of the limit. I'll have the limit as h goes to 0 of sine of h over h, but I can write that as sine of h minus sine of 0, because sine of 0 is just 0. And so now, to calculate the derivative of sine, I can pull this sine outside, just like I pulled the cosine. I need to know two limits. I need to know the derivative of cosine at 0 and the derivative of sine at 0. And I get cosine prime of 0 times sine of x plus cosine, plus sine prime of 0 cosine of x. And once you know those two limits, then you know everything. But you have to prove those limits, and those limits can be proven geometrically. So the real reason I wanted to just bring this up was how easy it is to accidentally assume things that you haven't proven yet. And if you want to use Taylor series, if you want to use L'Hopital's rule, to do that, you need to know that the derivative of sine is cosine, and that's essentially calculating this limit. Okay.
Why couldn't you say, like, we define sine to be the Taylor series of sine?
We're not economists. We don't, it's a question of what you want to define. If you do define the sine as the Taylor series, you can do that, and then this problem becomes trivial. And then the challenge is to show that your definition of sine recaptures the problem you want it to be.
I feel like I've seen we do that with E fairly regularly. Like we define E to be the Taylor series of 1 plus.
All right, so this is worth discussing, so I will, oops. Go into here. And so we're doing, okay, so I'm going to just add this into the slideshow. Okay. So if we have not done E in this class, correct?
No.
Okay. So there's two different ways to define the exponential function. Your e to the x is the limit as n goes to infinity of 1 plus x over n to the n, or it's the sum n goes from 0 to infinity of x to the n over n factorial. Either of these is fine. Can people see my screen right now or no?
No.
Okay. How about now?
Yes.
Okay, so these are the two definitions. And if you try to expand this using the binomial theorem, you can start to try to play some games to show that they're the same. What is e to the x times e to the y?
E to the x plus y.
Nope. I mean, yes, but technically what it is it's the sum, and it goes from 0 to infinity of x to the n over n factorial times the sum, m goes from 0 to infinity of y to the m over m factorial.
We did this as a problem.
Okay, I mean, we did do this as a problem.
We did do this, yeah.
Okay. And then you show, using the binomial theorem, that it is the same as e to the x plus y. And if you hadn't had this, then if this wasn't true, then our notation would be horrible. And then did we do the Baker-Campbell-Hausdorff theorem? Did I mention that at all?
No.
All right, so I'll let you look up what happens if you have e to the a, e to the b. Or sometimes instead they do like e to the ta, e to the sb, where a and b are matrices. Okay. So, go to, try to see if I can go back to showing slides. So one of the things that's annoying is the Zoom taskbar keeps dropping down in front of, okay. All right, so now by Poisson summation, we have our nice formula, and it turns out that given the inequalities on f and f hat, the only way this equation can hold is if f vanishes on lambda minus the 0, and f hat vanishes on lambda star minus 0. So it puts strong constraints on f and f hat, and the question is, what do these constraints mean, and can we determine candidate functions to try? And so the last line is the one that I really want to focus on. It is natural to try to guess f from our knowledge of our roots. For example, in one dimension we could try, and then somehow that seems to have been cut off. I don't know why. So let's go back to one dimension. And assume I tell you that we know a function vanishes at some points x1, x2, and so on. Does this uniquely determine f?
No.
No.
You can multiply by a constant.
So you can multiply by a constant. So what kind of case would you want to do first in terms of studying this?
Leading term is 1.
One is leading term is 1.
One root.
Sorry?
Only have one root.
Good, only have one root, excellent. And so I was a little bit more ambitious. I said only finitely many roots, but one root is the same. So if we only have finitely many roots, what's the solution?
Polynomial.
Polynomial. So does this have to be the solution?
It could be that times any non-zero function.
It could be times any non-zero function. So the answer is no. Now, what will you consider a non-zero function? If I give you the function 1 over 1 plus x squared, which is essentially the Cauchy density, is that a non-zero function?
Yes.
It gets really close to 0, but it doesn't
Are
get
we-
0.
Are we only assuming real functions?
I have been deliberately vague. So if you are considering only real inputs, then the Cauchy density 1 over 1 plus x squared is non-zero, and we could multiply by it. If, however, you allow complex values, then 1 over 1 plus x squared does not work, because if we take x to be plus or minus I, you'll be dividing by 0, and it will blow up. So depending on where you live, you have some freedom in terms of what g of x you could take. So any thoughts about what might happen if we allow infinitely many roots? What should the answer be morally?
No.
So we know the answer for finitely many zeros. What should the answer be if we have infinitely many zeros?
Also no.
Well, right, but you have a guess as to what it should be. How can we extend our answer for finitely many zeros?
We can again multiply by a non-zero function.
Okay, so what would the answer be? So f of x is g of x. So g of x will be non-zero, and then what comes after the g of x?
Weierstrass product, maybe?
Weierstrass product. So we would have some kind of infinite product. And so basically, you know, the xn's range through all the zeros, and we just have some function g. So is this right, or are there any issues in writing this down?
Do we know that that product will converge?
We don't. And so one of the themes to get out of this class is that whenever you see an infinity, you have to be careful and you have to justify convergence. And so here is one of the classic examples. Let's assume the xn's are just all the integers with multiplicity of 1. So in this case, it might be better to have the product going from minus infinity to infinity. And so if we try to do that, you know, we would guess, you know, maybe some g of x, and, you know, we'll figure out what the hell g of x can be later. But let's look at, for now, let's look at maybe, you know, h of x is the product and goes from minus infinity to infinity of 1 minus, there's a lot of different ways to do it. We'll do it, you know, x minus n. What are your thoughts about this product? Do you like this product? Why not?
Doesn't converge.
The terms aren't even bounded.
Yeah, the terms aren't even bounded. So if we take x equals 0, well, actually, then the product might even be 0 because we do have an x minus 0 term. We just have an x term. So you might be okay at 0. But if you take x to be 1/2, it's going to blow up. So we can't try this. So how could we fix this? What could we try next? I want something that has roots at the integers. So x minus n didn't work. What could we try?
X over n minus 1.
Sure, except I'll do 1
Yeah, x
over n. And so if I do that, now things are going to be good.
Oh, you could do 1 minus x over n to the n.
So we could raise it to a power, but then that would give you a multiple root. And so we wanted to have roots of order 1 at each integer. So we're trying to build this function. So what's your first thought when you see something like this?
Well, at 0, it's going to have problems. At n equals 0.
No, and
At x equals 0,
so what we'll do is we'll then say n is not allowed to be 0, and we'll just pull out an x like that. So good. So that fixes that issue. What other issues might we have?
Still ask whether it converges or not.
Yeah, so how would you figure out if this converges?
Maybe take a logarithm thing.
Yes, right. You know, if you're in a class with Miller and there's a product, take a logarithm. So the log of h of x would be, you know, the log of x plus the sum, and goes from minus infinity to infinity, and is not equal to 0 of the log of 1 minus x over n. Now the log of 1 minus x over n, what does that equal? the log of u, I'm sorry, log of 1 minus u is negative u minus u squared over 2 minus u cubed over 3, dot, dot, dot. So this would be negative x over n plus 1/2 x over n squared plus 1/3 x over n cubed, and so on and so on. So if I just naively sum, and I'm just going to play games and not really worry about being careful, do you think these sums over here are okay or not okay?
Okay.
So they're okay. So you have to do a little bit of work. Each one of them is fine, 1 over n squared, 1 over n cubed, 1 over n to the 4th. But then you have to worry about, you have infinitely many of these. And so I'll leave it as a game to you to prove that this is actually fine. So this converges for all x. And it's a nice game to try to prove that.
But the one on the left doesn't converge, right?
Well, that's what we're going to try to get to. You know, this part over here is fine and is not going to be any issue. For each fixed power, you know, the squares, the cubes, the fourth, each one of these converges, but then you have all of those sums. So you have to show that the sums of all this stuff is still going to converge, no matter what x is. So I'll leave that as an exercise. What's the problem over here?
We know 1 over n doesn't converge.
So 1 over n doesn't converge. But remember that this sum is really, n goes from minus infinity to where n does not equal to 0. So in some sense, you have positive and negative n can cancel each other. But you have to be very careful how you do this so that you can exploit the cancellation. And what we're doing here right now, it's a little bit hard to have the cancellation to exploit. Have you heard of the rearrangement theorem?
Is this if you rearrange an infinite sum, you can get a different infinite sum?
So if you're conditionally convergent, but not absolutely convergent, can rearrange to have any lim sup or limit. And what you can do is, since it's conditionally convergent, the sum converges, but the sum of the positive terms and the sum of the negative terms converge. So if you want the lim sup to be 17 and the lim in to be 3, you keep adding positive terms until you first go above, whoops, oh no, okay. Until you first go above 17, then you take negative terms until you first go below 3, then you take positive terms until you first go again above 17, and then negative terms until you first go back below 3, and you keep doing this. And as you keep doing this, you know, it's possible that when you go above 17, you go above by maybe more than you did the last time, but the amount you're going by, you can bound by a number that's getting smaller and smaller because the terms have to be going to 0 because it's conditionally convergent. And so you can rearrange and get anything you want. So when we have a sum like this from negative infinity to infinity, really you should be interpreting this as, you know, it's the limit as, oops, as a and b going to infinity of the sum from negative a to b and not equal to 0 of x over n. And if a equals b, then it's going to be fine and you'll have perfect cancellation. But if, so a equals b, you're okay. But if b equals twice a, you have trouble. Or if you have your b equals a squared, or a to the a, or something like that. So unfortunately, we can't just write down this product. So we want to fix, the product of 1 minus x over n. Any thoughts as to how we might fix it? Well, if you go back here, the problem was we wanted to have cancellation. We wanted to have the plus n and the minus n cancel. So how might we redo this product?
Maybe we explicitly like multiply the plus n and the minus n as
Yeah.
the same term.
Yeah, so let's put them together. So n goes from 1 to infinity, 1 minus x over n, and then 1 plus x over n. Let's put them next to each other. And then that will be, x times the product, n goes from 1 to infinity, of 1 minus x squared over n squared. And now if you look at that, that's much different. That's much better. And if you now try taking, the log of h of x, that'll give you the log of x plus the sum, and goes from 1 to infinity of the log of 1 minus x squared over n squared. And then this part here would be negative x squared over n squared plus 1/2 x squared over n squared squared plus 1/3 x squared over n squared cubed, and so on and so on. And so now, if we sum this n goes from 1 to infinity, we're going to get something that'll be absolutely fine. Okay. So the next thing is, if we tweak it a little bit, what if the xn's are just positive integers? So in that case, you would try, h of x is the product, and goes from 1 to infinity of 1 minus x over n. But what's the problem?
You have the same convergence issues.
Yeah, it doesn't converge. It's really nice to work with objects that exist. Objects that don't converge are not good choices. So we need to somehow weight each factor by something so that the product will converge, but we don't introduce new zeros. And so we revise, and we'll try h of x is the product, and it goes from 1 to infinity, 1 minus x over n, and now let's take e to the x over n. And the reason is if we do this, this is the product, and it goes from 1 to infinity, we get 1 minus x over n, and then if we expand out e to the x over n, that's going to be 1 plus x over n plus 1 over 2 factorial x squared over n squared plus 1 over 3 factorial x cubed over n cubed, and so on. And when you look at this, I can break this up into two factors. 1 minus x over n times 1 plus x over n. Well, that's not going to be too bad. That's going to just be 1 minus x squared over n squared, right? And now I have the 1 hits everything, so there'll be plus 1 times 1 over 2 factorial x squared over n squared plus dot dot dot. And then we have the minus x over n times everything, 1 over 2 factorial x squared over n squared plus dot dot dot. Well, you can see that all of this stuff over here is going to be nice. It's going to be, at least of size 1 over n squared. I'm sorry, at most of size like 1 over n squared, x squared over n squared, something like that. And so when you look at this and you take the log, it's essentially going to look like the product, and goes from 1 to infinity, 1 minus x squared over n squared plus, small. So small that it's going to be okay. So this leads to, one of the most beautiful theorems in mathematics, the Weierstrass factorization theorem. And so here, these functions En of z are called the elementary factors. And here, when n equals 0, it's just function 1 minus z. And then more generally, we start expanding over here. And this gives us some convergence assistance. And so you can write any function that is, entire. This means it's complex differentiable on the whole plane. It has some zeros, an, that are repeated according to some multiplicity. So you can write it as, some order vanishing at the central point, z equals 0, an exponential function, e to the g of z, where g is a nice differentiable function, and then the product of these factors. And so I know most of you have not seen complex analysis, but I just wanted to mention two great results related to this. So the first is the little Picard theorem that says if you have a function from the complex numbers to the complex numbers, and it is not constant, then the set of values that it assumes is either the entire complex plane or the plane minus a single point. And if you look at the function f of z equals e to the z, this is a function from the complex numbers to the complex numbers. Are there any values that this misses?
0.
Yep, so it's never 0, and it hits everything else. And so it's a nice exercise. It's not too bad to show if I give you some number w, you can figure out what z is so that e to the z equals w. There'll be infinitely many z's because every time you increase the imaginary part of z by 2 pi, you just return back to where you started. But it is absolutely amazing that you can miss at most 1 point if you are a complex valued function that is differentiable on the whole complex plane on all of C. So what would happen if I told you G misses 2 points? So G is from C to C, it's entire, so it's differentiable everywhere. And there exist 2 points not in the image of G. What must be true?
It's constant.
G is constant. This is extremely different from real analysis. If you take the Gaussian is infinite differentiable, but it misses every negative value. In fact, it's bounded. So your complex analysis is extremely different than real analysis. Okay, so I'm going to just give you a hint of what is to come for the last class. They unfortunately don't know how to use theorem 3.1 to match all the density bounds on higher dimension, but they've got some various results. And one of the things they're going to do is they're going to use a calculus of variations argument. So I'm curious, how many of you have ever seen calculus of variations? Okay, this is a phenomenally useful worldview. A lot of modern physics comes from taking a perspective inspired by this. And so this is worth seeing before we send you out into the world. And so for the last class, we will talk a little bit about calculus of variations, which is the last major ingredient coming into these proofs. All right.